Okay, now I'm going to solve the second problem in that assignment number 5. So this is also an illustration of the use of BVP4C, the boundary value problem solver. But what we're going to do now is deal with a problem that has two sets of coupled equations, and each one is second order. Okay, so we have effectively 4 first order equations that we need to develop. And these are the two equations, and these are the associated boundary conditions. So the first thing that we notice is the independent variable x has a range from 0 to 1. And at both these boundaries, the left boundary and the right boundary, at x equal to 0 and x equal to 1, we have u, the dependent variable, as 0. And also v, the dependent variable, is 0. And so we have 4 conditions, and we have a fourth order, effectively fourth order, or 4 first order equations. So our first task is to rewrite these equations in the form of a system of first order equations that are given here. So our task is basically to find f1, f2, f3, f4. Now the first question is it linear or non-linear? Obviously there is e to the power u, and u is the unknown, and e to the power v, and v is an unknown. So it is non-linear. Okay, is it an initial value problem or a boundary value problem? Because the conditions are given at 2 different locations, it is a boundary value problem. Okay, and reformulate the model equations. Okay, how do we do that? So we define 4 variables. y1 is equal to u, and y2 is equal to du dx, and y3 equals v, and y4 equals dv dx. Okay, so those are the 4 equations. So we need to get 4 variables, and we need to get 4 equations by simply taking the derivative. So dy1 dx is equal to du dx by taking the derivative here, and du dx is y2, so that is my first function f1. Okay, then dy2 dx is d square u dx square, and d square u dx square from this equation, move everything else to the right hand side and make the substitution that u is the same as y1 and v is the same as y3. So you will get lambda square e to the power y1 minus 5 lambda y1 minus y3. That is our second function f2. Okay, and then we need to get the third equation. The third equation is dy3 dx, which is equal to dv dx. But dv dx is y4 from the next definition. So that is my function 3. So function 1 is y2, function 3 is y4, function 2 is this expression that you see here. Similarly, we develop an expression for dy4 dx. Okay, I'm running out of space here. Let me do it here. dy4 dx is equal to d square from this one is equal to d square v dx square when you take the derivative of that. But d square v dx square, keep this on the left side, move everything else to the right hand side, is going to be equal to lambda square e to the power y3 minus 5 lambda y1 plus y3. That is the function 4. So we have obtained all the 4 functions. Now we are ready to go and program this in MATLAB. So once again, since it is already done in the previous case, I'm going to go through it somewhat more rapidly. We are asked to identify the solution for a whole range of parameters lambda from point 1 to 2 in steps of 0.05. That's a lot of solutions, but we can just set up a loop to do that. So let's first make sure that it works for one parameter value and then put a loop around it as we did before. And we're also asked to try in the last part to get a solution for lambda value of 4. It turns out that there is no solution for lambda value of 4 because there is something called a limit point, that there is no solution beyond that limit. And so the BVP4C should not converge. So we want to see what does it do when it encounters such a situation. But keep in mind, for the moment, we need to write these 4 functions and write a boundary function that evaluates these 4 boundary values. So let's go to MATLAB and edit a new file and call it as A5P2. I create that, and so I'm going to now create a function, and I will call this as f equals A5P2, and it's not going to have any input. Okay, sorry, it's going to have an input because it is a function that implements the 4 functions. It will have x and y, the independent variable and the dependent variable. Now here the comments I'm going to put are x is the independent variable and y is of length 4, consists of y1, y2, y3, y4, and is the dependent variable. We are of course interested only in y1, y3. y1 is u and y3 is v. We are interested only in those. y2 and y4 are its first derivatives. And there is a parameter in the problem. Okay, so now we can write the 4 functions. F is equal to, I'm going to write them as a column vector because that's what BVP4C expects. And these are, the first one is y2. Now, how is y2 defined? y2 is defined by this argument that comes into this function. Hit return to go to the next one, and the next function is a complicated function, which is lambda square e to the power y1 minus 5 lambda y1 minus y3. Okay, so let's do that. I'm going to call this as lambda as p, the parameter, p square multiplied by exp y1 minus 5 times p times y1 minus y3, enter. Okay, so it says that there is an error there because the exp is not matched. Okay, so y1 minus y3 is within parentheses, and the next one is y4. That's the third function. And the fourth function is lambda square, which in our case I'm calling it as p square, times exp y3. I need to put, I have an error there. That parenthesis should go there. And then there is an extra parenthesis there. Take that out. Okay, so e to the power y3 minus 5 times p times y1 plus y3. And close the brackets and put an end. And that should be the right function. Now it says that there are some errors in here. N or colon can only be used in indexed arrays. This might be an incorrect use. So there is something else that's wrong. Oh, I guess I have an unmatched parenthesis and then a square bracket. Then the end is fine. Okay. So that creates the function that calculates the four equations. Okay, then I'm going to write a function. These are going to be context of subfunctions, a function within a file. A5P2BC. And this takes YA and YB, like two vectors. YA is the value of the unknown Y1, Y2, Y3 on the left boundary, and YB is the same on the right boundary. Input argument YB might be unused. Well, we're going to use it. Okay, so let's ignore that warning message. And let me call this as fun, maybe. Okay, assignment 5, problem 2, function, and then the boundary condition. The boundary condition is going to be have to return a vector of length 4 because there are 4 conditions, and these are YA1, YB1, YA3, YB3, and end it there, and then put an end there. Okay, so that is your boundary condition. YA1 is the same as U at left boundary, and YB1 is the same as U at the right boundary. YA3 is V at the left boundary, YB represents V at the right boundary. Okay, so B represents the right boundary, and 1 and 3 represent the U and V variables. So we have written the two functions that we need to use with BVP4C. So the main thing to notice is that it's a fourth order equation. So there are 4 inputs coming into Y, and there are 4 functions going back. And similarly, there are 4 residual functions that go back to BVP4C. So these two functions will be called from BVP4C. Okay? So we can say sol equals BVP4C, and the function name A5P2 and then A5P2BC, and then sol INIT, the initial condition for the variable. Now, obviously we have to define that, and we have to define the x range also. So x goes from 0 in steps of 0.1 to 1, let's say. Okay, because the left we know that, and we are creating a vector in steps of 0.1 over that range, and in that range I want to initialize. So sol INIT is let me just go and check because I never remember these things. Okay, let me, oh my goodness, I don't know what happened here. Waiting for the computer to recover. Okay, so help BVP4C. Okay, so this, I'm just trying to recollect how do I set BVP INIT. Okay. Sol INIT is the structure that contains the initial condition and that is set with BVP INIT there. Okay, so I can go back to this function and say sol INIT equals BVP INIT x, comma, and the initial condition for the y vector. So I'm going to say 0, 0, 0, 0. Now notice that I'm giving you 4 values because there are 4 unknown functions, y1, y2, y3, y4. So these are supposed to be the initial guesses for those 4 values. And x is the independent variable that goes from the range of 0 to 1. And so I've defined the very minimum basic thing that is needed to solve this problem. And I would like to test it out to see whether it works. Now, there are some problems. There is a parameter p here. I haven't defined that yet. So I have to put a global p, and then I have to define this. Now, this has to be a function also because we're using the subfunction function. So function sol equals A5 P2, and there is no input argument. And global P. So P is the parameter that's going to go from the main function to the subfunction here. So I need to define a range of values for P. So the parameter set is a range of values are given, but I just want to test it out now with P is equal to 0.05, for example. Okay, so let me set a breakpoint there. Syntax errors, it says. Okay, where is the syntax error? Input argument X might be unused, although later one is used. Consider replacing it by, well, I don't need X because this function does not depend on X. And I can ignore that, that's just a warning. And here, terminate the statement with a semicolon, that's a good idea. And I should do the same thing there. And then, if you can see, an end might be missing, of course it is missing. Okay, so now I save that and it has become active. Okay, so I run the thing. And one more step, and it looks like it worked. There was no error message there. Okay, so I have a solution. So I can plot that solution. Okay, so one way of plotting, as I indicated earlier, is to take sol and plot and see what kind of plot it gives me. Because sol is a structure, it's not treating that nicely. So let's extract information from sol. So xx equals sol.x. Okay, and yy is equal to sol.y 1 comma colon. So now let's plot x's versus yy. So there is my solution. Okay, so one of the features that the script file has is to identify this and then increment the value near the cursor and evaluate the cell. But I guess we don't have the cell yet. So let's try to put a loop around now. Okay, so I'm going to define the entire vector P as equal to 0.5 or 0.5. Let me just check. I'm asked to solve for 0.1 to 2. Okay, so 0.1 in steps of 0.05 to 2. Okay, so that is the range of parameters for which I need to solve. So I'm going to set up a for loop for P is equal to PP. That means P would always have only one value, but it will take the set of values that are constructed in PP. Okay, and then I need to put an end to that loop. And I can put a semicolon there to suppress that printing. Okay, and I need to plot. Okay, and the plot has to be generated within this for loop. And I need two plots. I've been asked to generate two plots. So I need to set up a mechanism to create using subplot and then switch between those two plots. So I'm going to say subplot 2, 1, 1, hold, and then subplot 2, 1, 2, hold. Okay, so this 2, 1 here refers to the fact that I want 2 rows and 1 column. So it's one figure below the other. If I had it like 2, 2, it would mean I'm going to have 2 rows, 2 columns, 4 figures on 1 page. So the 1 here simply says that I'm going to have only 1 column, 2 rows, that is one below the other. If I had 1, 2, 1, 2, that would mean I will have 1 row and 2 columns. Okay, so I've set up the 2, and also let me create a figure handle So this will create two separate windows, figure 1 in one window and figure 2 in the other window. So figure 1 and subplot 2, 1, 1, 2, 1, 2. Okay, and inside this I want to say plot sol dot x comma sol dot y 1. So this plots x against y1. y1 is u, but I want this on subplot 2 on 1. So subplot 2 comma 1 comma 1. Okay, and then I want to switch to subplot 2 comma 1 comma 2. That is the second plot of the lower section. Here I want to plot solution x against solution y3 comma colon. Okay, so if this works, then I should get two graphs on one figure. There is one figure window in the interactive MATLAB session. Let's see whether this works. Okay, so here it sets up two figures. In figure 1, you can see there are two graphs, one below the other. And then I'm going to step through. So there is my first plot, and then there is my second plot. Okay, and now I can continue. So P is going to have the next value. I guess I started with 0. Okay, so that's probably a mistake. I should have started with 1. And let me clear the figures and clear the workspace and clear the command line. So I start with a clean slate. Okay, so let me do it again. So here I am. Okay, now I'm starting with point 1, so I get a reasonable graph, and then continue. It's not doing the graphs. I get only one graph at a time. Okay, so is it picking up the right value of P? Obviously, it is picking up the value of P. So one of the tricks that I said earlier I should use is take this sol in it and put it outside. Okay, and then take the converge solution and put it in sol in it as a better guess for the next round. That will help in speeding up the convergence. So all I'm doing is taking the converged result that is stored in here and putting it into sol in it. So when it goes to the next round, it'll pick up that value automatically. Okay, so let me save this. And I probably need a hold here. Hold on, so that I get all the graphs, in which case I probably don't need a hold there. Okay, so save that and try to run it now. Okay. Point 1, okay. Yeah. Point 1.5, okay. All right. So now it's going to work. So what is the value of P? One. .45. Okay, so I succeeded in creating the solution for the entire range of the parameter P going from point 1 to 2. Now the next part of the question is it asks us to plot the norm of U against lambda. Okay, so the lambda vector, I already have it in there. Okay, so I'm going to create outside of this loop a second figure. Okay, and then I'm going to have to create a second plot, and this plot will have pp, the norm, the pp parameter, which is a lambda, and a vector called norm u. But we haven't created that yet. Okay, so what we need to do is we need to put in here norm u is equal to a blank vector. Okay, and inside this solution, I need to say norm u is equal to norm u comma norm of sol y 1 end. So what this is going to do is every time it comes around, it's going to take the previous variable norm u and append to it one more value, which is calculated by taking the solution of u from this vector, passing it to the function called norm. And the norm basically measures the length of that vector and returns that one number. So this entire thing is going to return one number, which will be added to norm. And we will see how this works after I put in the breakpoint there so that we can track what happens. Okay, so this variable normally appears to change size. Of course, it changes size, which is good, which is what we want it to do. So initially starting with 0 length, it's just going to keep on increasing. Apparently, that's not a very efficient way of doing, because when you dynamically change the size of the vector, it takes more time, computational time. So what they are saying is, instead of, if you look at the message here, the variable norm u appears to change size on every loop iteration. Consider pre-allocating for speed. That simply means make its size a constant one. And we can do that because we know how many elements there are, length of p, because for every value of pp, we are going to have one value of norm. So we could do that, but if we do that, we have to put it right after that, because pp has to be defined before we can define. So this is not length, I should say 0. Okay, yeah. So it says create a vector called norm u consisting of only zeros of the length pp. So this is what pre-allocation means. So I'm pre-allocating the length of norm u so it doesn't change, increase every time. Now, here, of course, when I do this, I need to put it every time in the next position. So that becomes a problem. So the way to do that would be norm of count. Okay, and then I need to define a variable called count is equal to 1. Okay, and then I can say inside the loop after this, count equals count plus 1. So every time I'm incrementing in the loop, because the loop counter actually contains the values of the parameters, which are not necessarily integers, right? And so I'm setting up a separate counter, which is an integer, and then I'm incrementing it every time, because the, here, empty, should be equal to norm of sol dot y1 comma colon. Okay, so so norm u is the vector that we have created of length pp containing only zeros. Here, when I'm doing it for a particular count, I'm saying in that position, replace the 0 with the actual norm calculated from the solution vector. And then I have a counter here. Okay, so let me run this and see whether it produces the result that I want. Okay, so I'm going to set up a breakpoint there and clear this figure and then run. Okay, so here you see the first figure, and then it has plotted the two subplots, but norm of u itself contains so we are in trying to generate the second graph, which would plot the norm of the u vector, the solution, against lambda. So what we did was we initialized a vector of the length of pp. And let's just see what MATLAB will do if I just enter zeros, 1, 5. Okay, so it creates a row vector with 5 numbers. So if I use that format, zeros, 1, length of pp, whatever the length of pp happens to be, in this case I think it will be about 39, it will create 1 by 39, a row vector with 39 zeros in there. That's just initialization because we are avoiding by pre-allocating the memory to make it efficient. So then when it comes through the loop, I set up a counter. Initially it is 1. So the first array in norm will be replaced by the actual norm value calculated according to this. Then counter is increased and it goes back the second time around. It will replace the second vector. And I just want to demonstrate how that works. So here we have stopped right before it executes a norm. And at this stage, the norm vector should contain 39 zeros. Here it does. Okay, as step one more, the first position should contain the actual norm, 0.0091. Everything else should be 0. Okay, the count is now just 1. Now this is executed, so the count is 2. So I'm moving the pointer to the next array, and then I am solving for the next value of p, which is the second vector in pp. Okay, so pp is a vector of 39 length. These are all the parameter values for which we want to generate the solution. Okay, now I go through the loop again. I've added the second curve, as you can see on this side, and I've replaced the 2 elements in the norm u vector. So if you go through this, it will eventually replace all of them, and let's just complete that. And then it should create the second figure and plot the second figure as the norm against second figure, which is the norm of u against lambda. You can now put labels and titles and things like that for both the figures. Okay, so that is the solution essentially to the second problem. We have, I think, answered all of the questions that were supposed. No, we were asked to try for lambda of 4. Now we can try that, and then this outside of the loop and set p equal to 4, and then just get the solution for one more time. So just copy and paste this. Okay, and now you can see what happens in the MATLAB window. In the MATLAB window, let's close this window. Okay, so when I run this, I should get an error message corresponding to the very last situation. So it's busy, it's solving for all the cases. Well, it's done. Generated the first figure, and it's still busy. It's now trying to solve for the very last case. I think it must have generated both the figures. Yes. It's still busy. I think my computer is just slow. Let's wait some more time. There it is. Okay, so the second figure is created, and then it gives me the warning message that for the last value of the parameter lambda equal to 4, it's not able to meet the tolerance. That means it has not met the error criterion, so the result is not converged. And that was the last part that we were asked to do. Okay, let me stop this.